So this is where we talk about, rather than spinning plasmas, we talk about spinning off things, and we talk about magnets. Magnets being obviously the most, at the moment, the technology that is most associated with this new form of enthusiasm for fusion. And I have a very distinguished panel, and they will now introduce themselves, and then we'll get to work. Please.
Jonathan Toretta from TAE.
And just so briefly, what is TAE?
TAE is a field reverse configuration fusion company that's been around since 1998. We have built 5 machines, so you can actually come and see them. We're on our 6th generation machine.
Where do we come to?
You come to Orange County, California, Southern California. We have offices around the world. We'll get to that in a minute. And we've spun off 2 companies.
Mm-hmm. Chris.
So I'm Chris Good, physicist originally. I have a master's in physics from Oxford, but then went to the dark side, and I was an investor for about 20 years in a private equity fund. About 2 years ago, decided it was time to make a change, and I am now raising a fund called Pine Island, which is focused on the supply chains for fusion and for electrification. And so that's my objective right now.
I'm Francesco Volpe. I'm a physicist. I'm the founder of Renaissance Fusion and the CEO of Renaissance Fusion, which is a startup located in Grenoble, France, working on simplified stellarators with plasma-facing liquid metal walls and high-temperature superconducting magnets.
And Renaissance, since fusion hasn't had a naissance quite yet, why Renaissance?
Renaissance is actually about using the 2 halves of the brain, the artistic and the scientific side, and being creative while making science.
That's lovely.
So hi, I'm Antonio Pellecchia. I'm coming from Italy, and the company is called ASG Superconductors. Whoever is doing research in fusion knows us, but we are manufacturing superconducting magnets since forever, basically, and all the research center this side of the Atlantic run on our magnets. So thank you for having me today.
You're very welcome. And Itxaso.
Itxaso Ariza, Chief Technology Officer for Tokamak Energy. Tokamak Energy being the spherical tokamak company based in Oxford, spun out of UKEA 15 years ago. But we were one of the first to develop HTS, high-temperature superconducting technology as well, and we believe we are well leading in this subject.
So I wanted to start with that. We heard this morning that Commonwealth fusion systems have half the circumference of the world in high-temperature tape, high-temperature superconducting tape. How much do you need for your tokamak?
About the same, probably. Yeah, the supply chain for superconducting tape is scaling up. I believe 15, 12 years ago, one of the challenges was to actually get wood quality tape. But since about 10 years ago, all the suppliers are actually able to produce better tape. And with all the advancements that we have made in the design of the magnets, we're actually able to take in tape of more varied quality and perhaps less quality than some of the competition. We're able to model that and actually adapt the design to cope with, let's say, a broader range of quality of tape. So we believe that supply chain of tape is one of the constraints, but probably less so for us than for some of the competition.
Interesting. You're buying tape that's just not quite as good?
Absolutely.
Not quite as good as ASG could provide?
No. We don't produce HTS tape cables. The tapes that are produced are not perfect. Mm-hmm. So you got to live with the defects that come with it. A defect can lead the magnet to misfunction. Mm-hmm. So you got to design it in a way that it is working like the most damaged part of the HTS conductor, brought very trivially into words. So you got to downgrade the performance to make sure your magnets live to the let's say to the lowest point of performance of the entire length of conductor.
Or you can have technologies that actually acknowledge that there is some defects in the tape
and plan for that
and improve the magnet performance by creating alternative paths for the current so that you can cope with those defects without needing to downgrade your performance, which is perhaps what the strength that we have in Tokamak Energy. 10 years developing HTS magnets have developed not only the understanding of the tape, but also how you build very compact, very modular, very simple magnet designs that you can then scale up and cope with those defects without having to downgrade your expectations of the magnet system.
But it's not trivial. I mean, it's something
is.
very, very extraordinary to be achieved.
So you're dealing with it at some sort of like control system that you're changing things.
No, a lot of it is proprietary, but the way we manufacture the magnets, we are able to cope with small defects that perhaps in other HTS magnets and certainly in LTS, low temperature superconducting magnets, would have led to the magnets to fail. We're able to cope with those defects. We've actually drilled holes in magnets and found that there was no problem with the magnet function, a bit of a reduction in the performance. So we're able to take that tape and lead the current in a different way to cope with those defects. And that's basically what has led us to being able to make more compact magnets, reliable magnets that we believe now have got applications in other adjacent markets away from fusion, markets that perhaps were a bit nervous about LTS in the past, and markets that would be nervous about HTS. But whenever we talk to anybody in aerospace or in magnetic levitation trains, when they look at what we've done, they think actually the HTS time is now, but they're quite impressed by how we have solved in a simple way some of the technical challenges that HTS had before.
Francesco, I understand that you take a different approach because you actually make the superconductors in the magnets.
That's
through
right.
paper deposition.
And actually what we do is very related to what Antonio and Itxaso, I hope it's pronounced correctly, were referring to. So for us, it started as a necessity, becoming developers and producers of HTS tapes, not just of HTS magnets, because we have a radically different approach to making stellarator coils. Stellarator startups divide in two big families, one accepting the complexity of the coils and figuring out cheap ways of making 3D sculptures, and others, like ourselves, or TAE Energy, trying to simplify the coils. In our case, we are making big cylinders coated with superconductor, and we will engrave, in fact, we are already capable of engraving these big cylinders. So effectively, instead of making three-dimensional sculptures, we are making 2D engravings. We are painting on an HTS canvas with a laser brush, back to the artistic reference from before. And why is this relevant to this topic of the defects? Because in narrow tapes, you can have these defects clogging the current. And so, as Antonio was referring to, you need to design your coil based on the performance of these bottlenecks. Whereas if you have very wide HTS, as we need to, you get the bonus that now you have sparse defects here and there, but the current just slaloms through them and finds its way around the defects. And this has a potential impact on many other markets, not to mention the agility of drawing your circuit as opposed to winding hundreds of times. It's a faster, more elegant technique, similar to the changing paradigm from the single transistor to an integrated circuit.
So are you looking at those other markets for this broader?
Absolutely. And wherever, so the requirements of fusion are not unique to fusion. Wherever you need a large magnet, meaning you need to magnetize a large volume with a strong magnetic field and with high precision. So these three requirements are not unique to fusion. You meet them, for instance, in medical imaging, in energy storage, in magnets for accelerators, for wind energy, even for vehicles, for some electric vehicles. So these cylinders or large surfaces of HTS, engraved HTS, are applicable to all of these markets, and they provide an opportunity for revenue generation early on the way to fusion. So to make impact, to get a return on investment early on and bootstrap your future fusion business.
Jonathan, that sounds very much like what TAE has been doing over the last 7-8 years.
Yes, that's exactly right. I think the way that I put this in context is we didn't plan it this way. We've been at this since 1998. We built a very large IP stack. We got very good at doing things in-house. Building certain technologies ourselves, building a mini grid to run a 450 watt to 750 megawatt system. Part of that market came to us and said, can we sort of borrow this? And we said, at cost, you can. And so they're paying us for that. And then we spun that business out, and that's a business in its own right. And then precedent to that, something that we certainly didn't expect, was a cancer treatment business in the life sciences space through boron neutron capture therapy. If you're familiar with Sumitomo Health, that could be considered a competitor or maybe a peer to us in that space. We have a very advanced system that we also spun out. We are the largest owners of those businesses just by way of structuring, but they're businesses in their own right. They're managed separately from us. They have their own cap tables. They're non-distracting. I've had that conversation a couple of times today of whether or not, a company that's focused on fusion is distracted by the fact that it's got a life sciences business and a power solutions business. I would say by the fact that, again, those management teams and cap stacks are separate from us. I think they're non-distracting. But as Oliver and I've had the conversation separately as well, I think it just really comes down to structuring. If you structure it the right way, if you've got the right advice on it, I think it can be a successful strategy. And just the last thing I would mention too is, as this ecosystem forms, I think one of the things that you're going to see is investment by companies like us into our own supply chains, but then the suppliers also investing in companies like us. You're seeing a lot of sharing of resource. You're seeing a lot of seconding of resource between these companies. I would say the broad theme of today of ecosystems forming is absolutely right. But I'll stop there.
But I am interested. Maybe you could come on to this a little bit.
Sure.
What's the logic of maintaining of having them sort of like arm's length, but not spinning them all the way out?
So I'm going to try to put this in proper context. They are spun all the way out for addressing markets. We've wanted to retain, by way of returns back to our shareholders and by ways of returns back to the company, a hand on these businesses for the fact that they can help us fund our business. And we have raised, and it's in the public, more than $1.2 billion. But we've not returned that much capital to our shareholders. And again, 1998 is the start point for us. If we can return capital via these markets and via these businesses, we will do so. Extending this a little bit further as well, what we don't do is pursue every opportunity that comes our direction. So we've been proposed services companies. We were proposed something else for a public audience that we're not going to do. It's again, discipline, right? Just knowing which of these opportunities are the right ones, which ones have large addressable markets where there's non-binary risk, something Chris may speak to in a moment here, where you've got, a revenue build and a growth business into something that is a fusion-derived market, but not dependent on fusion being a success.
So, Antonio, I was struck that TAE is, by the standards of fusion companies, very old.
Yeah.
But ASG is older. You've been in...
It's ancient. Yes, absolutely. The company was founded 75 years ago. And of course, in the beginning, it was copper magnets. Then it developed into superconductivity. So currently, we do multiple things, a little bit like it was said a moment ago. We are supporting with our magnets research in fusion. We are collaborating with some of the startups in fusion in developing their magnetic confinement system. We are exploring what can be achieved today with LTS and what can be achieved tomorrow, but literally tomorrow, not 5 years ago, in the future with HTS, which is something we are working with today. So basically...
Is there still a vibrant market for LTS technologies?
LTS technologies are the superconducting magnet of today. So basically, all the MRI systems you see in the world are made with LTS technologies. All proton therapy systems around the world are done with LTS technologies. So basically, they are the superconducting technology today, whatever you would find in an hospital, for example. We are sticking to this trend to diversify our business and to not doing it in a crazy way. We are not trying to shoot at any target we are seeing. For example, our biggest development in the moment is using superconductivity and knowledge in superconductivity. You would call it MTS, medium critical temperature, which is magnesium diboride. It's another material. It's a compound made of very abundant elements in Europe, so you don't have to go to exotic places finding these elements in order to manufacture these kind of things. These are superconducting cables for power transmission. These two little things together can bring 20,000 amp from point A, point B, and we really think we got something with this one. This can affect the way we conceive our electric networks, our distribution networks. This might lead to, for example, connecting to land a windmill field offshore, or could be used, as Ross was saying this morning, to power up a data center, which is very energivore. So we are trying to concentrate on those applications of superconductivity that do promise to carry revenue in the very short term.
And magnesium diboride, what sort of temperature do I need to keep that?
24K. So it's colder than HTS, and this is a little bit of a pain, and as we all know, but it pays back in terms of ease of manufacturing, because as you will see, these kind of cables are manufactured with the same technology that is used for copper wiring. So it's not a technical challenge to develop conductors like it is for the tapes, and they do scale up much faster.
And what do you use as your refrigerant down at 25?
This is usually gaseous helium, but we are using, or we are planning to use also liquid hydrogen, for example. If you think of the environmental aware kind of transportation means in the future, like ships powered by hydrogen or trucks powered by hydrogen, you could conceive some fast chargers stations for a ship, for example. If you think of today, cruise ships do berth in the harbors with their diesel engine on, polluting cities. I mean, I live in a coastal city, so that's a problem I know very well. They could simply turn off the engine, being powered by a superconducting cable while tanking hydrogen for the cruise. So, I mean, there are a world of applications that we might think of.
Chris, a world of applications. This is the sort of thing that makes investors happy, yes?
Typically, yes. So I'd certainly say.
But in this case?
Oh, absolutely. In this case, I mean, I think it's stepping back and thinking about investors. There's a lot of different flavors of investors. At one end of the spectrum, you're seeing a lot of money pouring into the pure fusion technologies, which is fantastic. So you'll hear from Phil shortly, and Breakthrough Energy has been absolutely leading much of that investment into the technologies. Below that, though, all of that technology is trickling down into a supply chain and is really driving development, innovation within that supply chain. And that's where we, as growth investors, come in instead. So we're looking for technologies which already have a working product, shall we say, and a book of demand. And we're looking to put capital in to help them scale up. And that scale-up demand within HTS is enormous. I mean, today, roughly 90% of this HTS tape is being produced in places we really don't want to be buying it from. So it's from China, it's from Russian-backed entities. It's not an ideal...
Russian-backed entities meaning...
Japan. And it's not ideal for the future of what we need. And so there's a massive demand for Western countries to be investing behind this HTS tape to supply, because whether it's within fusion or it's in transmission, it's in data centers, whether it's in magnets for the use within medical machines, this material is going to be essential for the future of the world economy.
I was actually really, Francesco mentioned in some briefing discussions, superconducting gyrotrons for drilling deep boreholes for thermal, which just struck me as being completely wonderful. 1960s idea, just plunging them into the earth. But what are the obstacles to scaling up for these companies?
Well, I mean, we're focusing a lot on HTS here, but in the case of HTS, it's really hard to make. This stuff is very difficult. You're talking about, I mean, the superconducting material is a micron thick, and it's rare earth metals that have to be built in such or deposited in such a way that the crystalline nature of them means that they do actually they are superconductors. And let's not forget, a superconductor is something that will conduct electricity with no resistance. That means you would be able to transmit electricity over hundreds of miles without losing any of that power. Or energy, sorry. So that is a remarkable thing, and it is incredibly difficult to do. And so that's one of the biggest challenges, is just getting that technical engineering capability, which will work in a laboratory environment, into something that will generate thousands of kilometers of this tape on an annual basis. That's difficult. But you step outside of that and you look at things like lasers, for example. There's absolutely similar challenges within lasers. Within capacitors, within cryogenics, within vacuum pumps, all of these things that we're talking about that are needed within fusion, these are difficult things to do.
And is your investment entirely directed towards these ancillary technologies of fusion, or are you bought for that?
Our objective, what we're finding, and it comes back to what I was saying at the start, this trickle-down effect, where we're seeing These technologies are being driven forward by fusion, by the demands of fusion. And what you're finding is similar to the space race decades ago. You're finding all of these technologies are coming off and are going into all sorts of other industries you would never have expected. For us, the objective is to find places where you can make a good return on your investment based on those other markets, with the expectation that at some point fusion will become the dominant purchaser potentially of these, but you don't have to bet on precisely when.
Right.
You know, we can make a good return by looking at HTS tape that is being used for transmission, for example, which maybe is more straightforward and is going to be greater demand in the short term. So for us, it's about finding investments that are being driven forward by the fusion demands, where there are ancillary second markets where you can still make a good return on investment, but where there is still that sort of option value of fusion coming through at the end.
And do fusion startups understand the potentials of pivoting out of fusion? And have you seen other people taking the TAE route, Jonathan?
We've had this question come up many, many times, and I'm going to put it this way, and I'm going to quote a couple of the panels this morning. It's extremely hard. I've never had a job that's been this difficult. I think anyone on our team would say the same thing. And I think, look, I wish that all the sort of, as they're sometimes referred to, Gen 2 fusion companies have a lot of success, but they may not appreciate just how difficult it is. Our very large IP stack comes at the consequence of trying to solve problems that we just did not think we could solve. And I'm going to put it in sort of that sort of broad brushstroke, right? It's just that hard. But the problems are surmountable. We've overcome, our own sort of power management problems, and it became a derivative business. And again, not intended, but that was the consequence. Yeah, I hope that that's enough of an answer just to say I think it's daunting, but can be done. I think someone at Breakthrough said the hardest thing that they're doing is fusion, and I would completely agree with that. And I think everybody probably in this panel, everyone in this room would agree with that.
Why did you choose to work on the hardest problem?
I'm an engineer, and we love a challenge. I worked 20 years in aerospace, and it's also a complex field, but I believe fusion is the energy of tomorrow, and actually I believe that HTS technology can transform the world. And this complex situation where we have a division that is semi-independent team, magnetics developing HTS technology and superconducting technology, not only magnets, as well as fusion, was a very good challenge to actually see the synergies, but also the complementarity of the two. I agree, we have, I think it's over 250 patents on the HTS technologies themselves. A lot of them have been granted on the back of solutions to problems that were not in fusion. So HTS was developed for fusion initially because it had to have HTS. And then we tried to address problems in other markets that gave us access or identified problems for us that probably fusion will only identify in 20 years' time. And that made us fix those problems, and then we're spinning that back into fusion. So the challenge of do you spin out completely or not? I think there's a lot to be learned and cross-learned between fusion and the other applications of HTS technologies. So the right relationship is yet to be found. But for me, it's both HTS from a fusion and also from a non-fusion technology is literally the technology that will change the world, a bit like was said before.
Wonderful. So questions about the panel's various different positions on this. I'm looking out for... I can see a microphone. Oh, who do we have? Yes. Yes.
Yeah, I hope I'm not being too sort of pessimistic on this, but the time frames that you're talking about, the energy requirements we have coming along, given that there is solutions possibly like solar panels in space, beaming it down, microwave to the ground, if a solution like that comes, providing the quantities of energy that it could, how do you see that affecting your future with the demands of money that you need and 25 years looking away as a solution? Isn't there a time frame that something else is going to come along?
Hell of a question. Well, first of all, let's hope it happens. I mean, that would be already a fantastic thing. Well, it takes it takes money and it takes people to develop new segments of business. Magnets and whatever is related to magnets is unforgiving business. I mean, I think we all agree on this. There are things that are driving billions in the market today. MRI systems, for example, they are sold in the tens of thousands as of today. HTS, for example, is promising to open the market of rotary machines to superconductivity, enhancing the effectivity of engines or windmills and that kind of stuff. This is not, we are not looking at decades from today. We are looking at possibly years of development, years, and substantial investment in it. So possibly, if I could deliver a message to bring back to the various ventures capitalists in this room today, is that money does make a difference, especially when you are not I'd say a government-baked kind of company. At that moment, money can really accelerate your process of development because it makes you available people and tooling to complete the resources and partnering with big institutions as well.
Chris, would you see Pinetree as you wouldn't put yourself in the venture space, would you?
No, and I was about to make that point, which is reinforcing what you said. We're looking at a typical investment cycle, but we're looking for companies, so i.e. a sort of 3-4 year investment period and a 3-4 year realization period. So we're talking about things in the next 6 to 8 years that have to generate a return. And for us, a return involves revenue and ideally cash flow. So these are real businesses we're talking about. This isn't about a sort of pie in the sky kind of science experiment.
Right.
So that's why I think that there is real technology that is coming out of this, exactly as I was saying before, that is monetizable today and where you can generate a return today on the back of it. So whether or not fusion is 5, 10, 15, 20 years away, and I'm more at the shorter end than the longer end, to be clear, but whatever the timescale is, there is still places to be putting capital here that are fusion related that will generate a return.
And the microwave source of the question from the gentleman in the audience, that microwave source will require a magnet and most likely will be an HTS magnet.
Transmission somewhere.
So we will win anyway. I don't think in this panel we should compete with other energy sources. As someone in an earlier panel this morning said, one does not exclude the other. In fact, we need to have all of them. All energy sources, renewables, beaming, solar energy from space, you name it. This panel, I think, is more about competitions between HTS and other fusion-enabling technologies and alternatives out there. But HTS will really be a revolutionary material. It will, regardless of fusion, it will revolutionize geothermal, transmission of energy, storage of energy. So transport with levitated trains, so it will really be a game changer anyhow.
Okay, question down there.
So I spent my life in magnets, so I concur and support. And thank you, by the way, you're making a difference for accelerators as well, so it's very good. Now, curiosity from your side, you've been involved in magnet technologies, but also the other technologies which are crucial to fusion. Fuel cycle, tritium breeding, material withstanding radiation, and balance of plant, the cost. So of the other technologies, where do you see the impact on society and other applications?
That's a great question for 2 minutes left in the panel.
Yeah.
Jonathan.
Yeah, I'll try to tackle that in 80 seconds here. Well, okay, first of all, for the gentleman from CERN, he probably knows that the TAE is pursuing hydrogen boron. So some of the problems that we have are different than some of the technologies this morning. I mean, the application of what we're doing, I think, is akin to what Chris was saying earlier. And I bring it back to, again, sort of like the context of something that everybody in the room would appreciate. If you look at NASA, or if you look at something like SpaceX even, and you look at the types of technologies that were iterated and developed in the broad application, I think the answer is simply we don't know what all the applications are going to be and what's going to be created, down to things that are quite simple like handheld calculators, which were part of the development of the space race, cellophane, I mean, things that were developed, again, for a space application, but have an application in all of our houses today. I think the applications are just simply that broad. They could be basically applicable in any industry. But I think for you, given 9 seconds now, we could give you a very targeted list of the things that, for not for a 400-person or 50-person audience, whatever the audience is right now, that would kind of give you an indication of what the things are that we see on more of a physics basis.
But would it be safe to say, as a sort of like generalization, that in some sort of like double product that involves how crucial it is to fusion and how widespread it is outside, that's the sweet spot for high temperature superconductors in a way that it's, I mean, there are lots of people who need lasers.
Can I chip in? So just very quickly on the same question, the thing I would say is there's a whole range of these technologies within fusion that are monetizable outside of fusion. There's also some that are not. I mean, tritium handling, honestly, lithium blankets, etc. It's very hard for me to see what the applicability of those. Maybe there is. I don't know what it is today. And I think that just comes back to the funding, where it's going to come from. As a private investor, I'm very happy to look at those things that are monetizable outside of fusion. I think they're really exciting opportunities. The ones where it's more, where there are fewer opportunities, I think you're going to need to lean on public funding. And we need that mix of public and private funding. And some will be more heavily public, some will be more heavily private, I would say.
Francesco, you seem to want to...
Yeah, I mean, as the only person, I think, at this table working on liquid metals and answering your question with our bare hands. Materials coping with the harsh conditions of fusion can cope also with the harsh conditions of fission. And I see an avenue to transversal commercialization in SMRs and fast breeding reactors, transmutation, thorium, etc. So there are situations in which our product, not based on lithium, based on other materials like sodium, can be commercialized otherwise. Big science like CERN is another area in which you need shielding from neutrons or energetic particles, and in which liquid metal solutions are important. And then there is a plethora of completely unrelated subjects, completely unrelated markets, where you don't really bother about shielding the neutrons or breeding the tritium, but still what you learned to shield the neutrons and breed the tritium is applicable. One example, soft robotics. What does soft robotics have to do with fusion or with neutrons? Zero. But they both rely on liquid metals. When you learn how to control them in fusion, you can apply that to special robotic arms that mimic fluid movements of human bodies. So Boston Robotics is fantastic, but they still look like robots to me. One day, maybe we will have liquid metal-based robots, a spin-off for Renaissance Fusion, by the way.
There you go, liquid-based robots you didn't expect to get here. Thank you all very much indeed. It's been really inspiring. And please enjoy the rest of the day. We have one more. Yes.
Thank you,